హలో
హలో
వినపడుతుందండి మేడం?
సార్ వినిపిస్తాను సార్.
ఓకే ఓకే. నేను కనపడుతున్నానండి వీడియోలో కనపడుతున్నానా?
కనిపిస్తున్నారు సార్.
ఓకే అమ్మా. మెథడ్స్ క్లాస్కి వెళ్ళలేదా మీరు? మీ ఆప్షనల్ కాదా? అప్లైడ్ మ్యాథ్స్ ప్యూర్ మ్యాథ్స్ మీరు అప్లైడ్ మ్యాథ్స్ ప్యూర్ మ్యాథ్స్?
ప్యూర్ మ్యాథ్స్ సార్. ప్యూర్ మ్యాథ్స్.
మన వెంకటేశ్వర్లు చెప్పారు కదా క్లాస్?
చెప్పారు సార్.
ఓకే ఓకే. అప్లైడ్ మ్యాథ్స్ పిల్లలకి ఇంకా అవ్వలేదు అనుకుంటా, వాళ్ళు వచ్చాక మొదలు పెడతాం.
ఓకే.
ఎక్కడి నుంచి అమ్మా? ఏ సెంటర్ నుంచి మీరు?
నెల్లూరు సార్.
అబ్బా సరేనండి. నిన్న మొన్న అటెండ్ అయ్యారా? హావ్ యు అటెండెడ్ yesterday's classes?
నిన్న వచ్చాను సార్.
Oh, I see. Could you understand what I taught?
అర్థమవుతుంది కానీ కొంచెం ఫాస్ట్ అనిపిస్తాను సార్.
It is so because see actually you have a lot of portion, okay?
Yes, sir.
And I may not be able to cover the entire thing, and there are 18 chapters, right? And
yes,
for the Hyderabad and Secunderabad people, we have been teaching since April last week, okay?
Yes.
But still of course I try to be slow. I'll be doing 2 or 3 theorems in a day, but I do it slowly, okay?
Okay sir.
The point is you have to be thorough up to BSc minimum. If you can be so, then it becomes a bit fast to understand, okay?
Yes, sir.
We see whether that class is over or not. Zero 16 to 95. I'll see whether the class is over or not. Then after confirming that it is over, then I'll start this. Hello. Hello. Hello, friends. Hello.
Yes, sir.
Am I audible? Hello.
Yes, sir. You are audible, sir.
Okay, okay. Are you able to see me? Am I appearing?
Yes, sir. You are appearing.
Okay,
Yes,
okay.
sir.
I'll open whiteboard and come.
Sir, at the this time 2 links are available in the
Yes, yes. Yes,
yes, sir, same class.
yes, yes. What you are saying?
At a time 2 subjects are there. One is algebra and one is applied methods of applied mathematics. 2 is there at a time. 3 to 4.
This
3 to 4.
now I'm speaking on functional analysis.
Okay, sir. Thank you.
Yeah. This is fourth period, functional analysis. Okay. Functional analysis. Okay. This is session number 4 today, and today's date is 7/8/21. Okay. My name is SRINIVAS. Yeah. Can I start the lesson? Hello? Hello? May I start the lesson, friends?
Yes, sir. Yes, sir.
Okay. Well, yesterday, if you were there, we were discussing a theorem connected to bounded linear maps or continuous linear maps. Okay, continuous linear maps or linear transformations, right? If T is a mapping from a vector space N into a vector space N dash, and if these are normal linear spaces also, if you have norms also on these vector spaces, and these should be linear spaces on the same field F. Okay, either it is this reals, both are vector spaces, or the field of real numbers, or both are vector spaces or the field of complex numbers. Okay, or the same field, these two linear spaces must be taken, and T is a linear map. Okay, T is linear, means T of alpha x plus y is alpha times Tx plus T times y for all x comma y coming from this linear space, and alpha is coming from this field. Okay, then that map is called linear. Continuity means, in fact, this function is said to be continuous if a sequence xn is converging to x in n, if x belongs to n, and xn is a sequence converging to x, then this T must be taking xn's to T of x. Okay, right? You take an x in big N, and you take a sequence xn converging to x, and then if this function T takes xn's, that is T of xn's to T of x, we say that function T is continuous. This should happen for each and every sequence xn converging to x. Okay, and this is equivalent to saying this one. Right? Bounded linear maps. By bounded linear maps, we mean this. Bounded linear map. Okay, right? T is a linear map from N to N dash. We say this T is bounded if there exists a constraint M positive such that norm Tx is less than or equal to M times norm X for all X coming from N. Okay, Tx on N. So X a variable must be taken in the domain space N. Okay, so T of X is here. X is here. It is taken to T of X. T takes X to T of X. So T of X is in N dash. So this is the norm on N dash. Okay, and this is X is in N big N, And so this is the norm on n. These norms may be different or same. It depends on the context you take. Okay. So we suppress the suffixes for norms because we understand from the points inside. Okay. If x is coming from n, we take this norm, and if t of x, when you consider t of x, it is coming from n dash, we take the norm on n dash. Okay. So by bounded linear map, we mean this. If you can find a positive constant such that this is true, then for all x coming from big N, the linear space n, then we say this linear map is bounded. Okay, this need not be the definition, the term you use for a function is bounded. If you have f mapping n to n dash, if f is mapping n to n dash, what do we mean by f is bounded? When do you say f is bounded? If the f image, f of n, right, you take any element in this, okay, and norm y should be less than or equal to a constant. Okay, the same constant must be working for all y's coming in this from this set. Okay, means right, you have this n is some right, you have this n may be this, and this f is taking the elements here into n dash. Okay, into n dash. Right, this could be your n dash. Okay, and okay, n takes the points here to this one, and if you if these you take you can take the origin. Around origin you should take an open sphere of suitable radius m1. Okay, or if all y's lie in this, if all points in fn lie in this, then we say the function f is bounded. That is the usual meaning of a function is the boundedness of a function. But for linear maps, we define different boundedness. We are defining bounded linear maps. Means it is normed right by this inequality. By right, this adjective for linear map means this one. It need not be this boundedness. Okay, and in fact, in theorem 3 in the first theorem, in this unit 3, we showed that this is equivalent to saying that T of S is bounded. T of S is bounded. Okay, means what? Let me show you. Okay, what do we mean by T of S? What do we mean by T of S? Right, we are right. This is n. This is n. This is n dash. Okay, and T is mapping n to n dash, and we are saying bounded linear map. Okay, a bounded linear map means what? It is a linear map from n to n dash, right? And then this is linear, and this is linear, and by boundedness we mean there exists a positive constant m such that norm T of x is less than or equal to m times norm x. Okay, and this should happen for each x coming from n. Okay, for each x coming from n, this should happen. Okay, in fact, this is equivalent to showing that if you take S to be the closed unit sphere, if you take S to be the closed unit sphere, means x belonging to n, such that norm x is less than or equal to 1. Okay, this is the right. This is what? These are the points around origin whose distance from origin is less than or equal to 1. So here is origin. Around this, you are taking an open disk of radius 1 unit. Okay, this radius C is 1 unit. This radius is 1 unit. Okay, and if you take points x from here, if you take points x from here, okay, and whose distance from origin, if these lengths are less than 1, you have to collect all those x values. All of them will be lying in this. This is called closed unit sphere around a closed unit sphere. Unit speaks about the radius. Unit sphere around the origin. Okay, and we can show that this boundedness of linear map is equivalent to that. If S is this, then T of S is bounded. What do you mean by T of S? You take the T image of this. Okay, it may be something like this, right? You take S from here. You look at the corresponding. Images. You collect all of them. If let X vary over this S. Okay, this is the units closed unit sphere. Let X vary over this. You collect all T of X values, right? And then this is bounded. By boundedness, what do you mean? Around, right? 0 is taken to 0. 0 is taken to 0. This 0 is taken to 0. Okay, and then around 0, there will be some positive number M1 positive. Okay, around M1, you take a closed ball of radius M1. Okay, unit sphere. You take unit sphere of radius M1. Okay, and then if I right, these are T of X values. So norm T of X will be less than or equal to M1. That's what we mean by that T of S is bounded. T of S is bounded means you take X in S. Okay, look at T of X values, and they will be inside an open disk, inside a closed disk of radius M1. Okay, this is the disk. This is the disk. Inside this disk, right? These are all, of course, T of S values. These are all T of S values. Okay. T of, right? So T of S values, these will be lying inside this red colored open disk. Okay. So that's what we mean by the boundedness of this. This is a set. T of S is a set. S is a set. T of S is a set. Boundedness of a set, by boundedness of a set, we mean this one, this property. Okay, it's called boundedness of a set. So you should be careful while using these terms. This is the boundedness of linear map. Okay, for linear map, by boundedness, we must use this. Okay, we should be careful with definitions. So in the first theorem, we have that these two are equivalent. Yesterday, finally, we were proving this theorem. Okay, what were we proving? Right, we proved this theorem yesterday. Let T be mapping n to n dash be where n and n dash are normal linear spaces. Okay, and let this be linear and onto. Okay, then we showed that T is 1-to-1 and T inverse exists. T inverse is bounded. T inverse is bounded. If and only if there exists an small m positive such that m times norm x is less than or equal to norm tx for all x coming from n. Okay, this is what we proved yesterday. Okay, right. This speaks about the boundedness of this linear map. In fact, before this theorem, we proved that if T is linear, 1, 1, and on 2, T inverse is also linear. T is linear and surjection, and then you can show that T inverse is also so. T inverse is also linear and 1, 1, and on 2. Okay, and 1, 1, and on 2. This also you can show. This in fact we showed before this theorem, right? We showed that if T is linear 1, 1, and on 2, then T inverse is also linear, and from here we can show this. After that, we proved this theorem. Today I'll prove the I'll explain the last theorem of this unit 3, and then we'll enter the next chapter. Okay, yeah. So this is the last theorem of this unit. Can I move this a bit?
Sir, page number, sir.
Hello?
Page number, sir.
What you're saying?
Unit textbook page number, sir.
Functional analysis.
Sir, okay. Ante unit 3, sir.
Unit 3, I will tell you the page number. Wait.
Okay, sir. First 2 chapters అయిపోయా
I spoke for one session only. I will come back to the first 2 chapters again in the last 3 sessions. Okay.
Okay, sir.
I did not complete them fully. See, I tell you. Now I want to speak on 1 minute. Let me look at the theorem number. That is 3.4.3 on page 66. Theorem 3.4.3
Okay, sir.
on page 66. Okay. I want to speak on this theorem. Okay. In the first session, I spoke on the first unit and some right and second unit. Again, I will come back in my last 3-4 sessions. I will come back to units 1 to 3. Units 1 and 2. Okay. Now I am see, for the Twin Cities people, we have covered up to page 63. Okay, for Twin Cities people, right? So that's why yesterday I continued after from page 63. Okay, and for the other people I'll come. I spoke only for one session on these 2 units. Again, I'll come back in my last 3-4 sessions. I'll come back to units 1 and 2. Okay, and 1 to 3. The path for the portion from page 1 to 63. Again, I will come back in the last 3-4 sessions. Okay, that's what I want to do. So today I am starting. I want to discuss this theorem because for these Twin Cities people something should be new. That's what I am trying. Okay, otherwise they get bored. Okay, okay. Now right, which one? Right, this one. Now let me state this. Theorem. This speaks about let n comma n dash be normed linear spaces. Be normed linear spaces, right? And B of n comma n dash be the set of all continuous linear maps from n to n dash. Okay, right? N and n dash are normal linear spaces. B of n and dash, this is B. This is B, script B. Okay, script B. B of n and dash is the set of all continuous linear maps. Means these are bonded linear maps. These are bonded linear maps from n to n dash. You collect, there may be, for example, the constant maps, zero map is a bonded linear map. Every constant, right? The zero transformation, this zero map takes all elements x to 0. That is the zero transformation. Okay, that is the zero transformation. Right? Whatever be x, its image is 0. It is called the zero transformation, and that is one of these. And zero transformation can be seen to be linear, but it is bounded also. Okay. What is condition for boundedness? You should have an m positive such that norm tx is less than or equal to m times norm x. Okay. Here, if your t is 0, 0 of x is 0. This is 0. Norm value is 0, and if whatever be x, this is true. Whatever be m, right? Norm is non-negative. M into non-negative will be non-negative. This is always true. 0 is less than or equal to non-negative. This thing which is non-negative. Okay, this is always true. So that's how the and you can see that the zero transformation is a linear map. So it will be present. The zero transformation will be present in B of n and dash. Okay. So this is not an empty set. It is non-empty. And then we'll define a norm on this. We'll define on this class of B of n and dash. Okay. Yeah. Right. Then what? Okay. Define. Yeah. In fact, this we'll show that this is a linear map. This is a linear space. Okay. Which one shall I use? Erase it. Then B of n dash is a linear space. Okay. Here I assume n and n dash are linear spaces for the same field over field F. Okay, or the same field we take. These two must be linear spaces or the same field F. Okay, and then we'll show that this is also a linear space over F. Is linear space over F. Right, and then we define a norm on this linear space. Define norm T is equal to supremum of norm T of X such that X belongs to N and norm X is less than or equal to 1. Okay, this is how we define norm function. You define norm T to be this is definition. Okay, and we'll show that this defines a norm on this linear space. We'll show that this is a linear space, and we also show that this, if you define a norm like this, for every T belonging to this, we show that this becomes a norm on this linear space. Okay, define this, then norm T is a norm on B of n and dash. This is the theorem which I am going to discuss. Okay, so first we'll show that this is a linear space. This is a linear space. Okay, yeah. So proof. Let n comma n dash be linear spaces. Or the field the same field you must take, or the same field of real numbers or complex numbers. N is over R, for reals it is a linear space, n dash is a linear space over R. So the same field must be taken. Okay, yeah. Now consider consider B of n and dash. Okay, consider this. This is what this is defined as, right? T mapping n to n dash. T is linear and bounded. Okay, you collect the all bounded linear maps from n to n dash. Okay, such functions are T is a linear map. You collect bounded linear maps T from n to n dash, and this script B is formed of all such linear maps. Okay, yeah. Now we'll show that this is a linear map. This is a linear space. Claim P of n comma n dash is a linear space. Okay, yeah. How to show this is a linear space? We have to show that we have an addition with respect to which this is an abelian group, and we'll show that we have a scalar multiplication on this, and with respect to the using that scalar multiplication and addition, we'll show that multiplication is distributive and addition is also distributive over multiplication. Okay, yeah. So let us take two functions from here. This is proof of claim. Let T comma V belong to, or let me take S here, otherwise. Okay, I'll take S. Right. Let T comma S belong to B of n. I'm taking two elements from this. Okay, I will define an addition on these numbers, on these elements. Okay, define T plus S. Okay, T plus is a function. We define T plus of, because it's a function is defined by defining its values at each of the points X of the domain. Okay, so you consider T plus S of X for X coming from this. We define this as T of X plus S of X for all X coming from N. Okay, this is called point-wise operations. We want to define T plus S for T and S are coming from B of n comma n dash. What is script B of n comma n dash? It is a set of bounded linear maps. These are functions. Okay, so you take two functions from B and try to define their sum. Their sum also is a function. In fact, for the sum function, to define some function, you have to define each value of this sum function at each point of the domain. So you take x from n, okay, and you evaluate this function at x, okay, and this value is defined as t value at x plus s value at x. You can calculate t value at x and then s value at x, you add them, okay. So x is here, you can calculate t of x, and s is also here, so s is defined on n. You can calculate s of x. These are elements in n dash. In n dash, these two are elements in n dash, and n dash is a linear space. You can add two elements of n dash. Okay, so this is well defined. This addition is the addition in n dash. Okay, this is called pointwise operation. Okay, then we define. First, let us show that with respect to this addition, this is an abelian group. Okay. Now, if you now you consider t plus s of x. First, I'll show a commutativity. Right now, t plus s of x is equal to t of x. By definition, this is t of x plus s of x. This is definition. Okay, and tx, sx are coming from this. Right? If x is here, t of x will be here. If s is here, x is here, s of x will be here. So these two are elements here, and this is abelian group with this addition. So you can interchange. This is s of x plus t of x. Okay, and this is equal to s plus t of x. This is equal to s plus t of x. Yeah. Okay. So this is equal to s plus t of x. Right? If you are right, you operate each of these on x, s of x, and then t of x. You add these two. To get this, you add these two values. Okay. So you showed that t plus s of x is s plus t of x. Therefore, this is true for all x. X is any general element in n. Therefore, t plus s is equal to s plus t. Okay. Therefore, addition is commutative here. Therefore, right? Therefore, plus is commutative. Before that, in fact, we should show that it is closed. Before showing this, we must show, let us show that it is closed. I will show that the t plus s is again a member here. Okay, we'll first show that t plus s is closed, and then we'll come back. You may look at this. You may look into this. Yeah. T plus s belongs to script b of n n dash. Okay, I have taken two elements t comma s in script n n dash. First, let us show that. Okay. First, let us show that. Yeah. T and s are coming from n and n dash. B of n n dash. First, we'll show that t plus s is closed. Okay. The sum of these two elements is present here. This will show how t and s are bounded linear maps. We'll show that this also is bounded in linear map. Okay. So first, let us show that this is linear. T plus s is linear. Right. This one claim. T plus s is linear. To check this is linear, how? You take alpha x plus y, beta y. Okay. To check a function is linear, you consider alpha x plus beta y. You can take beta equal to 1 also because of alpha. Alpha is any scalar. X and y are coming from n. Okay. So let x comma y belong to n and alpha come from the field. Okay. N and n dash are vector spaces over F. Okay. Now you consider this. This is T of this alpha x plus y plus S of this, that is S of alpha x plus y. Okay. Now this is what? This is right. T is linear. So this becomes how much? Alpha times Tx plus Ty. Right? Because T is linear, T of alpha x is alpha times Tx plus T of y. T of x plus y is T of x plus T of y because T is linear. Similarly, this becomes alpha times Sx plus S. Okay. Yeah. because S is linear, this is alpha x plus, the S image of alpha x plus y is S of alpha x plus S of y. S of alpha x becomes alpha times Sx because S is linear. Okay. Now you can interchange these two. Why? T of y is present in n dash and Sx is present in n dash and alpha times Sx is present in n dash. In n dash, W1 plus W2 is W2 plus W1. Addition is commutative. So from that you have alpha Tx plus, this can be written as alpha Sx plus T of y plus Sy. Why? Since plus is commutative. Plus is commutative in n dash. Okay? Because of this. Because in n dash is a linear space. These two can be interchanged. It is commutative. Okay? These two can be interchanged. Now you can take alpha common between these two. This is alpha into Tx plus alpha plus Sx. Why? Because this is a vector space. N dash is a vector space. Alpha can be taken out. Okay? from the definition of vector space, this sum of these two is this. Similarly, this is what? This is T plus S of y. This is right. Sum of these two is T plus S of y. That's how this is pointwise operation. Okay. T plus S of y is T of y plus S of y. So this can be written as this one. Now this is what? Alpha into this can be written as T plus S of x. Pointwise operation. Okay. Right? What is T plus S of x? You can calculate Tx and Sx, add them. So this T plus S of x is this one. So for this you can write T plus S of x. Okay. Plus T plus S of y. Okay. So we started with T plus S of the alpha x plus y, and it is equal to alpha times T plus S of x plus T plus S of y. Okay. Therefore, T plus S is linear. We showed that this is a linear map. Is a linear map. And what else we need to show? We need to show that this linear map is bounded. Okay. Yeah. So next we show that claim T plus S is bounded. If it is bounded, then it will be here. These are not only linear maps, a set of linear maps, and they should be bounded also. So boundedness must be shown. Okay. Yeah. Now, right? T plus S is bounded. How to show? Boundedness means continuity. We have to show T plus S is continuous. For linear maps, continuity and boundedness are both same. Okay. So we will show that T plus S is continuous. Yeah. How to show? So in fact, it is equivalent to continuity at origin. Okay. Continuous at origin. Okay. So let a sequence X converges to 0. Okay. T plus S is a mapping from n to n dash. Origin will be here. This is A2 identity in n. To that, we'll take a sequence converging to 0. In Xn, in n, we take a sequence Xn converging to 0. So let this converge to 0. Now, our T and S are continuous. T and S, T comma S belong to P of n and dash. Means what? Means T comma S are bounded. Or continuous. Both are same. Okay, these are continuous linear maps. So what happens? Bounded or continuous. Okay. So the T image of this will be going to T image of this. Therefore, T of Xn goes to T of 0. What is T of 0? Is 0. Similarly, S is continuous. So S of Xn goes to S of 0. Okay. What is S of 0? S is linear. So this will be 0. So now you add these two. So T of Xn plus Xn goes to T of 0 plus 0. That is 0 plus 0. Okay. Sum of these two goes to sum of these two. Now what? This is what? T plus S of Xn. This goes to 0. 0 plus 0 is 0. So we started with a sequence converging to 0, and we applied. If you apply T plus S on this, how about T plus S of 0? This is T plus S of 0. Because T plus S is linear. 0 can be written as t plus s of 0. Okay. So we started with the sequence xn converges to 0. We are able to show that t plus s of xn also converges to t plus s of 0. Therefore, t plus s is bounded linear map. Okay, it is a continuous linear map. Therefore, t plus s belongs to script n comma n dash. Okay, so t plus is a closed binary operation on this linear space. Okay, previously I showed that this plus c is commutative. Okay, let us prove the other properties. So t plus s belongs to the script of n and dash. Okay, therefore plus c is closed. Therefore, right, this plus is closed on this linear space. This set of n and dash. Okay, we also proved that this plus is commutative. Right, on this set n comma n dash. Okay, we have to right, and then let us show the additive identity. Right, we'll consider the zero transformation belonging to b of n and dash. Right, where this is the zero linear map mapping n to n dash. What is zero linear map? It takes every element to 0. What is the zero linear map? It takes every element in x to 0. Okay, so that is called the zero linear map. You can show that it is linear map, right? And it is continuous also. It is zero continuous linear map. It is bounded also. Okay, so that is why it will be present in. Okay, and this works as the additive identity with respect to for this edition. Okay, we have right t plus 0 equal to t for all t belonging to script b of n and dash. This I want to claim. I want to prove this. How to show this function is this function? You calculate this at a general point. T plus theta of x, right? Is what? T of x plus theta of x. Okay, this is a point-wise operation. To operate this function at this point, you operate individually t at x and then theta at x, add them. Okay, the t of x. What is theta of x? It takes this is theta function. It takes right. It takes 0 x to 0. So this is 0. Theta of x is 0. So if 0 is the additive identity in n dash. So if you add 0 to tx, you get tx only. Okay. So t plus theta of x is t of x. Therefore, t plus theta t. You don't need to prove theta plus t because we showed that this plus is commutative. Okay. So it is enough to show t plus theta x equal tx. You don't need to show theta plus t of x is also tx. The other part by interchanging these two need not be shown because of this. Okay, this is another property of right additive identity property. Yeah, for all t. Now let us look at the inverse part, additive inverse part. Okay, you look at this function minus t of x. How do we define the additive inverse of this? It is minus t. How do we define this? It is minus of tx. Right? For linear operator, linear function t, we can define minus t like this. You apply t on x and take negative. This is an element in n dash. For n dash, you take additive inverse minus tx. Okay, that's how we define this. This is the definition of minus t. We'll show that this minus t is additive inverse of t. Okay, yeah. So claim minus t, right? Claim t plus minus t is equal to 0. Right? This means that minus t is additive inverse of t. Okay, we want to show this. So again, these are two functions. This is zero function, and this is this sum function, SGM sum function. So to check two sum functions are equal, you operate them you operate them on the domain. These work on these apply on n. Okay, the maps from n to n dash. Okay, so operate them on n. So for x belonging to n, what do you have? T plus minus t of x is what? This is t of x plus minus t of x. Okay, t of x plus minus t of x. And what do we mean by this? This is t of x. What is the meaning of this? It is plus into minus of tx is plus minus tx. Okay, minus t of x means minus of tx. That's how we define minus t. Okay, now plus into this is how much? This is t of x. Right? This is additive inverse of this. Therefore, this will be 0. This is the 0 in n dash. Okay. This is what? This is equal to 0 is 0 of x. Okay. 0 can be written as 0 of x. Now what? For this function at x is the value of 0 function at x. Therefore, t plus minus t plus minus t is equal to this 0 function. Okay. So we claimed that this is inverse of this. Okay. We showed the closure of this addition, and then commutativity we showed commutativity. Okay, and then we showed additive identity we showed, and then inverse additive inverse also we showed. Therefore, right, associativity remains. If we can show that, this becomes an abelian group. B of n dash becomes an abelian group with respect to this addition. So to show additive identity, we take 3 functions t u v. Let t comma s comma v belong to B of n dash. Okay. Claim t plus s of x plus v is equal to t plus s of v. Okay, t plus s of v. Okay. Right. T plus s of v. Now, again, this is associativity of addition on B of n dash. Okay. So this is a function. This is a function. We show 2 functions are equal. Apply them on the general element of the domain n. Okay. Yeah. So t plus s of plus v of x. Apply this on x. Okay. This is what t plus s acting on x plus v acting on x. Okay. And again, this is sum of 2 functions. This can be written as t of x plus s of x. Okay. T plus s of x is what? T of x plus s of x plus v of x. Now, where are these tx, sx, vx? These are coming from n dash. And in n dash, addition is associative. This is the addition in n dash. And this is associative. So this can be written as t of x plus s of x plus v of x. Okay. Because in n dash, these are elements in n dash, tx, sx, vx. These are elements in n dash. These are maps from n to n dash. So these are elements in n dash. X is element in n. So these will be elements in n dash. So in n dash, this is associativity. T plus s plus v equal t plus s plus v. Okay. So by that, I am able to write like this. And this is what? This is t of x plus, this can be written as s plus v of x. Okay. This is t of x. This is what? S plus v of x. Okay. Now this can be written as t plus s plus v of x. Okay. So this x can be taken out. T plus s plus v of x. This means what? The t plus s plus v is t plus s plus v. Means we proved this. Okay. So that's how we get the associativity of plus. So that's how this becomes an abelian group. Okay. Therefore, B of n dash and a plus is abelian group. Okay, and then you have to define a scalar multiplication. Okay, from where to where? From f cross nn dash bnn dash into bnn dash. Okay, we should be able to define a scalar multiplication from this Cartesian product into this. Okay, you take a scalar from here and a vector from here. Okay, the Cartesian product, alpha comes from f and t comes from the linear bounded linear map comes from this. Okay, this must be taken to alpha dot t. Okay, this scalar product takes this Cartesian product to alpha dot t. We have to define this. How can we define? You act it on x. Okay, this is defined as alpha into t of x. Right? See, alpha dot t is a linear is a bounded linear map. Alpha is a scalar. We have to define this linear this one as a suitable function. How do we define? You apply t on x, and this is scalar. This is an element in n dash. In n dash, vectors can be multiplied by scalars. So this is the scalar multiplication in n dash. This is right. This we are defining newly. Okay, this is a new scalar multiplication. Now, if you define like this, okay, we can show that this is a bounded, right? No. We have to show that this is a bounded linear map. We have to show that this is a bounded linear map whenever t is here. Okay, so claim alpha dot t belongs to right, this one, beta of n dash. Okay, right? We have, this must be here. Okay, so we define the meaning of this, and we have to show that this belongs to this. Okay, that's what I am trying for. We have to show that we have to exhibit that this is this. Okay, alpha dot t. What is alpha dot t of x? First of all, you have to show that this is a linear map. Okay, so apply it on alpha x. Did we show this? No. Previously, we showed t plus s of x only, right? We showed t plus s is linear. We showed t plus s is linear. We did not talk about the scalar product. Okay, how we'll do that? Yeah. So we'll show that this is linear. So you consider on cx c times x plus y. You apply it, right? You take elements x and y from n and a scalar c in the field. Okay, and you apply this on this element. So this is alpha dot t of cx plus alpha dot t of y. Alpha dot t of y. Okay, and this is alpha dot t of cx, right? Alpha into, you apply t on c of x, plus this is what alpha, right? This is alpha into tx and y. Okay, you apply t on y, multiply this vector by this scalar. Okay, now this is equal to, this is what t is linear. So this c comes out. This is alpha into c t of x plus this is what alpha dot t into y, alpha into ty. Okay, now this c can be taken out because these alpha and c are coming from field, and in field this multiplication is the multiplication in field. In field, multiplication is commutative. So alpha dot c is c dot alpha. So here you get c into alpha into tx. Okay, and then plus alpha y. Yeah, plus alpha dot ty. Okay, now this is what you can take what? Okay, this is c into right? C into T. This is what? This is alpha dot T of X. Alpha dot T of X plus this is what? Alpha dot T of Y. Okay, this is alpha dot T of Y. Okay, so we applied alpha dot T on this. C can be taken out. It is alpha dot of X, alpha dot T of X plus alpha dot T of Y. Therefore, alpha dot T is a linear map. Is linear. Is a linear. Therefore, alpha dot T is linear from n to n dash. Okay, we have to show that it is bounded also. Okay, let us show that it is bounded. So alpha dot T is bounded. It is bounded linear map. We already shown it is a linear map. We have to show it is bounded. How to show boundedness? So see. What is alpha dot T? What is, how to define the norm of this? Norm alpha dot T is supremum of norm alpha dot T of X, such that norm X is less than or equal to 1 and X belongs to N. Okay, how is this defined? Alpha dot T, norm of alpha dot T is supremum of norm alpha dot T at X, where X is coming from N and norm X is less than or equal to 1. On this closed sphere, unit sphere, this if you take sup, that is defined as norm. Okay, this norm. This is what? Supremum. All right. This norm, this is what? Norm alpha into T of X. As this happens. Okay. Right. Alpha dot T of X is what? Alpha, it is alpha into T of X. Now this is scalar, this can be taken out. It comes out as modulus. So this is supremum mod alpha norm T of X. Okay. This alpha comes out, it becomes mod alpha. When it comes out, it becomes mod. Okay. And here variable is X. So this mod alpha is independent of, this is constant. It is independent of X. This can be taken out. So this is mod alpha supremum norm Tx, such that this happens. X, norm X less than or equal to 1 and X belongs to N. So this is what? This is norm T. So this is mod alpha norm T. Okay. So norm of this is this, and this is finite. Norm T is finite because T is bounded. This is a finite quantity. Therefore, this is finite. Norm, because T is bounded, this is a finite quantity. Mod alpha is finite. Therefore, this is finite. That's how this becomes bounded. Okay. Therefore, alpha dot T is bounded. So that's how alpha dot T belongs to script B of n and dash. Okay. So scalar multiplication is closed on this. Okay. And then, okay, scalar multiplication is closed on script n and dash. So what else is remaining to show? You have to show that alpha plus gamma of T, alpha of T plus gamma of T. This you have to show. Okay. And then what else? Alpha into alpha dot T plus S is equal to alpha dot T plus alpha dot S. As I have done, you can complete these. Okay. You evaluated the single points X and then show that this is equal to this. Okay. And then the final one, the penultimate one is this alpha beta of T is equal to alpha into beta T. This I am not doing. Okay. You can do. As I have done, you can do this. And the final one is this 1 dot T is equal to T. Okay. This also you can show. How? You calculate this 1 dot T at X. This is how much? This is 1 into T of X. Okay. 1 dot T is defined as 1 into T of X. Okay. This is the multiplication. This is the scalar multiplication in n dash. T of X is in n dash. 1 is scalar. So this is equal to T of X because since n dash is linear space. From the definition of linear space, this is equal to this. Okay. So the 1 dot t at x value is same as t at x value. Therefore, you have this. Therefore, you have this. Okay. Similarly, you have to check these three. I'm giving this as homework. Okay. You complete this, and in the exam, you have to work out this. Okay. Yeah. Now we'll show that norm t is a norm. Right. We have defined norm t is equal to sup of norm t of x, such that x belongs to n and norm x is less than or equal to 1. We'll show that this is a norm. Okay, claim this is a norm. Norm t is a norm. Okay, on n. Okay, on what? No, on b of n and dash. Okay, t is coming from this b of n and dash. Okay, how? See, first of all, you have to show that this is non-negative. Norm tx values. This is supreme of all this. Norm tx. Right, for all this kind of x. So for x belonging to n and norm x less than or equal to 1, norm tx, you consider this. For norm values are always non-negative. Okay, norm of anything is non-negative. If you take supremum of this, if you take supremum of all these norm values, those also will be negative, non-negative, because each is individually non-negative. Supremum of all these values will be non-negative. That's how norm t is non-negative. Okay, and then next property is let norm t be 0. Okay, let this be 0. This means what? Supremum of this one, norm tx, as that x belongs to n, norm x is less than or equal to 1 is 0. Okay, I have written norm t. This is norm t. On the closed unit sphere, you take the norm tx values, take the supremum of them. This is sup. Okay, yeah. Now what this means? Supremum is greater than or equal to t of x. Supremum is greater than or equal to t of x. Supremum is greater than or equal to each of the individual entries. So norm tx must be 0. Right? We are showing, right? Yeah. So we showed that norm t is greater than or equal to 0. Okay. Norm t is greater than or equal to 0. We showed, and now norm t sup of the sup is taken over all these values. What are individual values? Norm tx. So this sup is greater than each individual value. So this is, yeah, okay. So this is less than or equal to sup of all these values. Norm tx, as that x belongs to n and norm x is less than or equal to 1. Okay, which is equal to 0. From here, I have written this, and the supremum of this is greater than or equal to norm of this. Okay, now, and this is always greater than or equal to 0. Norm values are always greater than or equal to 0. So between 0, norm tx values lie. This implies tx is 0. Okay, simple, right? Between 0 and 0, 0 is less than or equal to this is less than or equal to 0. That is why norm tx must be 0. Okay, if norm tx is 0 means tx is 0. Okay, means t is the 0 map. T is the 0 linear map. Okay, if t is the 0 linear map, 0 of x will be 0. This implies norm of 0 will be 0. This implies if tx is 0 for all these x values, now sup of all these will be 0. Okay, and if sup is 0, this is 0, so this is 0. So that's how norm t equal to 0 if and only if t is 0. Okay, so norm t is 0. No, I should take 0. Norm t is 0 if and only if t is the 0 map. Okay, this way forward. Number 2, we have to show the this thing. Norm alpha times t is mod alpha norm t. Previously I showed, right? Yeah, here I showed norm of alpha t is mod alpha norm t. So from this, you have this. Okay, this is scalar norm of scalar product. number 3 is triangle inequality. Norm T plus S is what? Is supremum of norm T plus S of X. Does that? X belongs to N and norm X is less than or equal to 1. Okay. Norm of T plus S is defined as this one. Now, this is what? Supremum of, right? This is what? T of X plus S of X. Okay. T plus S of X is T of X plus S of X. Now, this is supremum. Now, norm of A plus B is less than or equal to, yeah, norm of A plus B, right? Norm Tx plus Sx, right? Norm of A plus B is less than or equal to norm A plus norm B. By triangle inequality, if you call this A and this is B, norm of A plus B is less than or equal to norm A plus norm B. This is triangle inequality of norm. Okay, now you take sup throughout. So supremum for all these X you take. So sup of this will be less than or equal to sup of this norm Tx plus sup of this norm Sx. Okay, you take supremum throughout. Supremum of this will be less than or equal to supremum of this plus supremum of this. Okay, now supremum along all for all these X you take. Now this is norm, right? You are taking supremum of, right? Yes, like X belongs to N, right? X belongs to N and norm X is less than or equal to 1. Okay, now this is nothing but is norm T plus S. This is norm T plus S. It is less than or equal to, this is norm T and this is norm S. Okay, so that's how you can obtain the triangle inequality. Okay, therefore your norm, this norm is a norm on B of NN. Okay, therefore norm T is a norm on B of NN dash. Okay, of course I don't remember whether I wrote, yeah, B of NN dash is complete or not. Yeah, so in this statement I don't remember. Let me add what statement I wrote. Linear space, define this, then you can have if N dash is complete, so is B of NN dash. If this image space, if this image normal linear space is complete, this also will be complete. So the completeness of this depends on the completeness of this. Why? Because the norm is defined in terms of the images of T of X. T is coming from this one. T is acting on points X of N. So T of X values are coming from N dash. So norm is defined and the norm values of T of X values. T of X values are lying in N dash. That is why if in case your N dash is complete, this also becomes complete. Complete means what? You take any Cauchy sequence in this, it is convergent. If every Cauchy sequence in a linear space is convergent, we say that linear space is complete. Okay, so now we assume that this is complete, and we'll try to show that this is complete. Yeah. So let N dash be a Banach space, be complete. If a normal linear space is complete, we say it is a Banach space. Okay, let N dash be complete. Claim B of NN dash is complete. Okay, let me have some water. Yeah, how to show completeness? How to show completeness? What do we mean by completeness? You take any Cauchy sequence in this. You take any Cauchy sequence in this and show that it is convergent. So, how to show a certain linear space is complete? You take a now this is a normal linear space. How to show this normal linear space is complete? You take a Cauchy sequence in this, okay, and show that it is convergent. So let let Tn belonging to B of n, comma n dash be convergent. Right? Yeah. Be Cauchy, I'm sorry. You take a Cauchy sequence. You take a Cauchy sequence in this. Well, our aim is to show that this is convergent. Okay. So you take a Cauchy sequence in this. What do we mean by Cauchy? So what is the meaning of Cauchy? Right? We are starting with a Cauchy sequence. We'll show that this Cauchy sequence is convergent. Means we have to show that there exists a T belongs to B of n and dash such that this Tn converges to T in the norm in this. We define a norm on this. In that norm, we'll show that this sequence converges to T. Okay, that's our objective. Okay, what is the meaning of this? When do we say this is Cauchy? So for every epsilon positive, right, there exists an n naught belonging to n, such that for all n comma m greater than or equal to n naught, right, norm Tn minus Tm is less than epsilon. Okay, what is the meaning that Tn is Cauchy? For every epsilon positive, there exists a natural number n naught such that for all n comma m greater than or equal to n naught, the distance between Tn and Tm in norm will be less than epsilon. This is the norm in this space. Okay, that's what we mean by Cauchy. After sufficient, right, leaving a finite number of suffix values for everything else, for right, leaving the first T1, T2 up to Tn naught minus 1 for between every other pair of Tn values, for the difference, the norm must be less than epsilon. Means they must be sufficiently close. Okay, or they will be arbitrarily close. Okay, so this we have now. Yeah. What is the meaning of this? What is the meaning of this? Right? Yeah. Now, for x belonging to n, right? What is this norm? Tnx minus tmx. Right? This is less than or equal to supremum of norm Tn minus Tnx minus tmx, right? Yeah. This is what? Tn of x minus Tm of x, where x varies over this for x belongs to n. Okay, and okay, x belongs to n. See, you may recall what do we mean by the bondedness? But T belongs to B of n and dash means what? This can be written as that there exists an m positive so that norm Tx is less than or equal to m times norm x, right? And if you take, you can take m, the infimum or all these m's. It is infimum norm T. So this we proved yesterday. So this is less than or equal to norm T of x. Less than or equal to, in place of this, you can replace this by infimum, which is norm T. Okay, so norm T of x is always a norm T to norm x, because right, if your T is a bounded map, this happens, and you collect all such m's, you take infimum, that is gamma. Gamma is equivalent to norm T, so this can be replaced by norm T. So this always you have for all each T, you have this. So this is nothing but norm of this one. Okay, so right, this is what yeah. So right now, what can I say? Now we are taking look at the previous page. Yeah, you consider this value. Norm of Tn minus Tm is less than epsilon. What does this give? Supremum of norm of Tn minus Tm of x is less than epsilon. Okay, you consider this. So norm Tn minus Tm is what? It is supremum of norm. This is norm Tn of x minus Tm of x, right? Such that this is norm of Tn of x minus Tm of x such that what happens? X belongs to and norm okay. Norm Tn minus Tm is defined by this, isn't it? You calculate this function at x, where x is varying in n, and let x vary over this. Okay. By definition, this is equal to this one. And because Tn is Cauchy, this is less than epsilon. So, so for epsilon positive, there exists n naught belonging to n, such that n naught belonging to n. This is natural numbers. N naught belongs such that norm of Tn minus Tm is less than epsilon. Okay. So for the for all n greater than or equal to n comma m greater than or equal to n naught. Okay. Now you consider these nm values, nm values. Okay. So for n comma m greater than or equal to n naught, so this is less than epsilon. Okay. So this sup value will be less than epsilon, and because of this, so this will be less than this, which is less than epsilon. So this can be written as less than epsilon. This is equal to this is less than epsilon. So this is less than epsilon. Okay. So these values will be less than epsilon. So for this nm, norm Tnx minus Tmx is less than epsilon. Okay. So for nm greater than n naught, this is the difference between the norm of this difference between Tn and Tm of x values is less than epsilon. What this means? This means that Tn of x is Cauchy. Where are these coming from? These are coming from n dash. This, right? Tn is a mapping from n to n dash. So these are in n dash, and because of this, your this sequence Tn is Cauchy, and we are assuming that n dash is complete. Therefore, this Cauchy sequence converges. N dash is complete. N dash is complete. Please switch off your mic. N dash is complete implies Tnx converges to some T of x. There exists a T of x, right? Mapping from n to n dash. Okay, n dash is complete means what? These Tnx are convergent. These Tnx are convergent to a function T of x, mapping n to n dash. Okay, we'll show that this T of x is linear. T is bonded linear. T is bonded linear. Okay, that is one step. Then we'll show that in fact, we'll show that right. Please switch off your mic. Somebody is switching on mic. We'll show that Tn converges to T in the norm T on B of n dash. Okay, this will show. Okay, first we'll show T is linear, bounded linear, and then we'll show that the sequence of linear maps to Tn's converges to T. Okay, we have that Tn's are Cauchy. So Tn is Cauchy, that we have. So let us show this. Please switch off your mic. T is bounded and linear. Yeah. Let us show T is linear. So let us consider T of plus. Please switch off your mic. Somebody is. Hello. We are 6 people and we are not able to make it. Sonia is talking, I think. Sonia. Hello, Sonia.
Yeah.
Hello. Yeah. Who is that? Sonia is talking, I think. Please switch off. Okay. Now, what is this? T of x is defined as limit Tn of x for n. Okay. Now we'll show that this T is linear. So you consider T of alpha x plus y. This is limit Tn of alpha x, Tn of alpha x plus y. Okay, for n. This is limit of Tn of this Tn is linear, so it is alpha times Tn of x plus Tn of y for n, right? And then this is equal to limit of, if these are individually existing, limit of Tn and limit of Tn. Limit of Tnx exists, limit of Tny exists. So that is why, and alpha is independent of n. You can take alpha out. This is limit alpha into limit Tnx plus for n plus limit Tny. Okay, because these are existing. Limit Tnx exists, limit Tny exists. Okay, it is converted into T of x. So this is T of x. This is alpha times T of x plus this is T of y for n. This is T of y. So that's how our function T of alpha xy is linear. Therefore, T is linear. Okay, we have to show that T is bounded. We have to show that T is bounded. Okay, why it should be bounded? See, we are saying norm of Tn, norm of Tn is Cauchy. Right? Tn is Cauchy. We assume Tn is Cauchy. Okay, Tn is Cauchy. So every quotient sequence is bounded. Therefore, norm Tn is bounded. Okay, because right previously what we showed, limit of Tnx is T of x. T of x is limit of Tnx. So you take norm of this. Norm Tx is norm of limit of Tnx. And norm is continuous function. So this is limit of norm Tnx for n. Okay. And this is less than or equal to, and norm Tnx is less than or equal to norm Tn into norm x. Because your Tn's are bounded, norm Tnx is less than norm Tn into norm x. And you can take limit of this will be less than or equal to limit of this. Now your Tn is Cauchy, so these are bounded. You can assume these are less than or equal to m. You can assume there is this m positive such that norm Tn is less than or equal to m. So this will be less than or equal to m. So limit m or n, right, into norm x. Now this is m can be taken out. This is m times norm x. Okay, there is no, this can be replaced by constant m because your norm Tn's are bounded. Okay, so that's how norm Tx is less than or equal to m times norm x. Norm Tx is less than or equal to m times norm x for all x in n. Okay, therefore T is in the B of n dash. Okay, T is in B of n dash. So we showed that T is linear. Here we show that T is linear, and we also showed that T is bounded. Okay, T is bounded. Therefore, T is here. Okay, and then because our Tn is Cauchy, we can show that norm, right? Tn converges to T in norm. Okay, we can show that norm Tn converges to norm T. That we can show. Tomorrow I will do that, and then we'll enter the next chapter. I will stop here. Okay. Do you have any questions? Hello. Hello, friends.
Sir, thank you, sir. But all this is available recorded. So
this is recorded. You please make your own notes with from the recording. Okay.
Okay, sir.
I'm not able to make any pre-made notes. Okay.
Okay, sir. Okay, sir.
I'll continue. I'll show that the Tn's are converging. I will show that Tns are converging to T in norm. Okay, that completes this theorem. Okay, so tomorrow I will continue. Anything else?
Thanks, sir.
Right. Thank you. Goodbye.
Thank you, sir.
Can I stop here? Can I stop here?
Yes, sir.
Okay, okay. Goodbye.
Goodbye, sir.